What's up guys, in today's video I'm going to teach you and I'm going to show you how to create a tree data structure. This is very cool and this is very useful because with trees you can have a lower complexity regarding time when you search, when you insert, etc. Why am I saying this? Because for example, in the worst case in which you are searching for an element, the worst case is that the complexity is log base 2 of n, being n the number of elements in the tree. And this is something very useful. So for example, let me show you something. If we look for a binary tree, let's see if I found, this one. So for example, if we look for the element 14, you can see that we are not going to do many comparisons. So for example, we are going to do 1, 2, 3, and 4. So in the worst case, in a list of 14 elements, we are just going to make 4 comparisons. And this is something very, very big. And this is the reason why it is so useful. And why did I say that is log base 2 of n? So for example, let me logarithm calculator. Let me look for a calculator of logs. And here what we are going to do is that log of base 2 of 14. And you can see, well, we did 4 and here is 3.8. But for example, let's go for another tree, this one. And in this one we have 32 elements. So if we look for the 31 element, we are going to make 1, 2, 3, 4, and 5 comparisons. So here, if I put 32, we calculate and we see that the result is 5, meaning that in the worst case, we are always going to have just 5 comparisons. And this is why this is so useful. So, knowing this, let's build the binary tree. And how do we do this? Let me go to Visual Studio Code. Let me close this. And how do we do this? It is very simple. First of all, let's define the structure of a node. So how do we define the structure of the node? So the first thing that we have to do is to define the structure. And here we are going to put struct node. We will give another name later. And here we are going to say that the node is going to contain, first of all, the data, and here you could do a lot of things. So for example, you could say that the data you want is a string, a structure, or whatever, a void pointer, whatever you want. But here, in order to make it simpler, I'm going to say that the data is just an integer. So we put here this as the data, and now I have to use this same structure to refer to the node, well, to the left node and to the right node. Because as I said, this is a binary tree, and what binary means is that each node contains as maximum 2 childs. So for example, we are going to use this name because it's the name that we are going to put later. So the node, we have here a pointer to the left child, and we also have here a pointer to the right child. So next thing, well, here you can see that I have some files defined, and in the node h file, the next thing that we need to do is to first give that name that I told you. So we are going to say here type def struct node is equal to node, and then what we are going to do is to define the prototype of some function. So for example, we are going to say that we want a basic function to initialize a node that is going to give us the pointer that points to the space in memory in which we initialize the node, and we need more things. So for example, we need another function to destroy a node. So here we are going to call this node destroy, and we just need to send the node, and here we don't need to return anything. You could return, for example, an enumeration that you do for saying if it's an error or whatever, but yeah, here we are going to make it very simple. So the next thing is to create a function to add a node, and here inside this function we are going to initialize the other node that we want to add. So we just need to get the data, but we also need to get the node in which we want to add something. So for example, if you want to add a right child, we need to get this node in which we are going to add that. So we put this n, and here we are going to say that this is the data. So knowing that we have these functions defined, we will define them later. The next thing that we need to do is to define the tree. And as you can see here, I have a tree file defined. So let's first define the structure of the tree, and you're going to see that we don't need much. So for example, again, let's do the same. Tree, this is the provisional name, and here we are going to say that the tree only contains one thing, which is the root node, the first node. So here we are going to see that this is the root. You could also save here the height of the tree or whatever, but in this case we are just going to put the node. But this is giving us errors because it's saying, hey, what is node? So since I have this defined here, what I need to do in this file is that I need to include the node h. But we are not going to do this here. We are going to say that we are going to use, well, we are going to include the tree file, and inside the tree file, oh wow, I defined this in the tree file and this should be in the node h. Okay, well, this is from whatever. So here in this file, what I need to say is what we talked about. So for example, we are going to include the node.h file in which we have that. And then here we are going to change the name of the structure. We are going to say that the tree is going to be called tree. And here we are going to define some primitive functions. So the first one is the one that is going to initialize the tree. So here this one is going to be called tree init. And then the next one is a function to destroy the tree. So we have to call this tree destroy. Then the next one is a function to add a node to the tree. And as we said before, well, here I forgot that I have to send the tree that I want to destroy. But continuing with the other function, as I said before, we are just going to use the data that we want to add. So here what I need to say is that, okay, we are going to use the tree t, and then we are going to receive also the data. So, okay, now we have a problem here because I forgot that I need to include the node.h. And yeah, now everything is okay, and let's continue. So we are going to first define the functions of the node, and the thing that we need to do now is to define the initialization. So let me copy all this, and now we are going to put this here, and we are going to define the functions. So this first one is very simple. First of all, we are going to declare a pointer, which is the pointer that we are going to return, and it's going to be initialized to null. Then the next thing that we need to do, well, here this is giving me errors because I need to include some other libraries, and is the standard library, and also we are going to use the input output, although I think we don't need it because we are not going to print the tree, but yeah, let's include it anyways. And here we are going to say that the pointer n is going to point to a place in memory that we are going to reserve. How? By calling the malloc function. First of all, we have to do a cast, and we call the function malloc, and here we need to say the size. So we are just going to give it the size of a node. So here we have the size of a node, and now let's do a little bit of error handling. So let's say if n is equal to null, if the operative system said, hey, I cannot do this, we are going to fprintf to the standard error output, hey, error in node init. So yeah, we needed the standard input output library, and then we are going to return null because this was an error. Then the next thing is that we need to initialize the data, and we can say one thing. We can say that whenever we initialize a node, we can add data. So let's do that. So whenever we initialize a node here, we are going to also receive the data. I have to change this in the node h file. So here is the data, and I go here and I include this. So now we initialize the data, but we also need to initialize the left and the right child. And since we are not going to add anything now, we are going to set this to null. And let me also initialize the other one. And we can say that this right one is going to be initialized to null. So now the only thing that we need to return is the actual node. So we put here n, and that's it. We finished with this function. Now the next one, destroy. So if we receive a node to destroy, we have to be careful, because imagine that we have, for example, let me put this here. We have here a node A. Well, oh my god. A. Here we have the node B. And here, oh my god, here I have the node C. If I delete the node A, I lose the access to the node B and C. So what I need to do is that I always need to go first to the end, to the childs, to the leaves of the node. A leaf is a node that doesn't have any child, and those leaves are going to be the first ones to be deleted. So for example, I would delete first the B, then I would delete the C, and then I would delete the A. Once the A is a leaf, it can be removed. So let's do this. How do we do this? We do this by using recursive function. And what is a recursive function? It's a function that calls itself. So for example, we are going to put here node destroy, and we are going to call it on this same node. Well, not this same node. We are going to use, for example, first delete the left, and we are also going to call this to later delete the right node. So as you can see, imagine this. If we have the node A and we call this, okay, we would be here, and then we would send here to node destroy the node B. So now it would come here, and yeah, we haven't finished because I remember that I have to define this and equal to null. We have to define in every recursive function, we need to define a base case, and this is the base case in which nothing happens. Later, let me put a comment here, destroy. Later we would destroy that, but let me go on again. So here we receive the node A. It is not null. So we go here and we try to destroy the node B, which was at the left. So then we are here in the node B, it is not null, so we try to destroy the node at the left. And in this case, once we send this, it is null because there is no node. So this returns, and then it goes to the right of the node B, and it doesn't have anything. So it returns, and then after checking that the child doesn't have any, after checking that the node doesn't have any child, we can then come here and destroy. So how do we destroy? It is very simple. We just call the function free with the node, and that's it. So this is the destroy function. It is something very simple, but it can be very, very difficult to understand at the beginning. So now what we need to do is to add data. And it's a good practice, I think, that we always check if the node is not null, because imagine that we try to add something to a null pointer, it will say, hey, segmentation fault, and we would have a problem. So now the next thing that we need to do is to check where do we put the data, at the left or at the right, and what is the criteria followed in binary trees usually. So in this case, what we are going to do is that if we have a node here and this node contains, for example, a 4, and we receive a 3, since the number is smaller, it is going to be at the left. So imagine that at the left we had 2. So now, since 3 is bigger than 2, it would be at the right. So we would add this new node at the right of the 2. So let's do that. And how do we do this? If the data we receive is bigger than the than the data of this node, so what we are going to do is that we are going to put this at the right. So we say that the right is going to contain a node that we are going to initialize now that we send the data. But we have a problem here. We are setting this pointer without checking if there's a zone. a right child. In case there's a right child, we have a problem because we would be overwriting that child, and we don't want that. What we want is to check if node right is equal to null. It means that there's no child, right child. We can do this. We can change the value of the right node. But in any other case, what we need to do is to go to that right child and add that new node in the childs of the child. So for example, let's do this. We put here node add, and in this case, we send the right node. We put here the right node and we send again the data. Okay, so we have to do now the same for the left child. So here we would put else if the data is less or equal than this data. We are going to say, okay, let me copy all this because it's almost the same but without the right. So we put here left, and that's it. So now we are doing the same thing but for the left child, and we have actually finished with the nodes. What we need to do now is to implement the tree. So let's go and do that. Let's come to the tree.c, let's put here a semicolon, and now let's put the new function called, the function that is going to initialize the tree. So how do we do this? As we said before, here we have these prototypes, and this function is not going to receive anything, so we are not going to do any change. And okay, the first thing that we have to do is to first create a pointer of this tree. So for example, we are going to initialize this to null, and the next thing that we have to do now is to, okay, here, this is saying me that this null is wrong, because I also have to include these libraries. Okay, let me copy this because I'm having issues. So let's include this here, and now everything is okay. And we have to initialize again the tree. So in this case, we are going to do the same, and is that we are going to call the malloc function. So we initialize a space of memory in which we are going to have our tree. So here we are going to say, okay, we are going to do a cast to tree pointer because remember, malloc returns a void pointer. So malloc, and we give it the size, which is the size of tree. So now we are going to check if the initialization was okay by doing if t is equal to null. We have a problem, and we are going to say this in the standard error output. So here we put stdr, and we are going to say error in tree init. So that's it, and we return nothing. So we put here null, and okay. Now we have to initialize this, and since here we don't send the node, what we are going to do is that we are going to say that the root at the beginning is null. Then the next thing that we need to do is to finally return the tree. So that's it. That's how you initialize the tree. But now we have to destroy the tree, but the work is almost done. We don't need many things. So for example, we just need to say if t is equal to null. What we are going to do is that we are going to return because we don't want to destroy an empty tree, and we just have to access the root and then call the function node destroy, and this function will do everything. So let me explain better this function, and you will understand this with a draw. So for example, let's look for a paint because the paint here in Ubuntu is not very good. So let's say that we have a node here, a node here, and a node here, and one here. So what we are going to do is that, for example, if we call tree destroy, tree is going to call node destroy on this element. It's going to say, hey, do I have any child? I'm going to call nodeDestroy on this element. Since this is not null, this one is going to do the same. Do I have any child? I'm going to call nodeDestroy on this element. So this is going to do the same. But this one doesn't have any child. So it's going to send this to this. It's going to call nodeDestroy to this child, but this child is null. So it is going to return. Then we will call this on this one. It is null, so we will return that, and then we will destroy this. So since we have destroyed this one is now a leaf. So it is going to call destroy on the right one, and it is going to see that there's no right node. So this will return, and here now we destroy this one. Then we come here, we go to this, we try to destroy the right one, and we do again the same. It comes here, return, come here, return, we destroy this one, and now we just only have this one. So here it comes and se finí. So that's what we are going to do here. And it is as simple as just calling here nodeDestroy on the root node, and the nodeDestroy function is going to do all that. So we are almost finished. Here, the next thing that we need to do is to then destroy the actual tree structure. So we just have to put here free t, and that's it. Now, next thing. The next thing that we need to do is to add a node. And how do we add a node? Again, we have all the work done. So for example, if we put here, well, first of all, we have to check that the tree isn't null. If t is null, then we return and we don't do anything. But if not, we have to check one thing. Do we have a root node? In case we don't have it, we need to add a new root node. So here we are going to say if troot is equal to null, the next thing that we are going to do is to say troot is going to be equal to node init, and then we need to send the data. So we initialize this with the data. And we could check the error. So for example, we could say if troot is equal to null, then we return, and yeah, we could print an error, but we are not going to do this now. So the next thing is that, well, here let me put a comment. There's no child. Here we could say, hey, what if there's a child? It is as simple as saying, okay, in this case, I just want you to call the node add function on the root node. And that's it. It is as simple as doing this. So now what we can do is that we can create a main function to add a lot of nodes, and I'm going to show you, if I haven't, the Valgrind thing to check if we have any memory leak. So printing a tree is something more like way more complex, and I'm not going to do this in a video. So I'm just going to check if that everything is initialized, and trust me, this structure is fine. Like everything here is fine. So here, let me see why this is telling me that this is an error. Well, I have to send also the data, I forgot. So yeah, now everything is okay. So now what we are going to do is that we are going to create a main function in which we are going to say, okay, int main here, and we just need to import one file, which is the tree file. So the tree.h, because the tree file calls all the node functions, so we don't need the other functions. So here, well, we don't need the node functions. So here what we are going to do is that first we need to initialize a tree. So we put this here, tree init, and here we are going to say tree add node, and let's do this a lot of times. So for example, boom. Let's try that is not the same number. 3, 4, 5, 6, 7, 8, 9, and 10. So yeah, I need to also send the tree, and yeah, we have this here. And finally, I need to destroy the tree. So here what we are going to do is that we are going to call the tree destroy function that is also going to destroy all the nodes. Here we return 0, and I think we are finished. So now I'm going to show you how to use Valgrind, and first of all, let's compile and do this. So we are here in the terminal, and the first thing that we need to do is to compile the main file. So now here, what we can do is that we can compile all the files. So in order to do that, we can do gcc -c of all the C files. So we can do this by doing here. We have a lot of O files, and here we are going to create the executable by calling this. Let's call this exe, and we are going to use the main.o. Well, in fact, we can do this. So we use this, and now we execute the exe, and of course we don't have anything printed, and we don't know if everything worked fine. So what we can do is that we can use Valgrind. So we can use Valgrind --, I think it was check -leak equal full, and then we put this. So I think I was wrong. This is the other way around. Check leak. Okay, so now. And you can see that this is very useful because we are seeing that we are doing 11 allocations, and we are also doing 11 frees. Let's, for example, remove this line. So if we come here and we compile everything again, we create the executable, and then we execute Valgrind, you see that, for example, it's in here, hey, you allocated 11 times, but here you haven't done any free, so there's a problem, and it's telling you where do you have the problem. So for example, it's telling me that, hey, when you call in main the function 3init, you have there a big problem because there is a memory loss. So this is Valgrind, and it's something very, very, very useful. I don't know if I already have done this in any video, but yeah. So this is how you create a binary tree in C. And if you enjoyed the video, give it a like, share, subscribe, and see you in the next one.